Our last speaker is Nima Rasekh, who, after univalent bi-categories, will talk about univalent double categories.
All right. Before I start, let me mention that everything I say is joint work with Benedikt Ahrens, who is right there in the back. And of course, Paige North and Nils van der Weide, who are not here. Also, let me thank you all for still being here at like 5 p.m. It's quite late. It's very impressive. So, and of course, thanks to the organizers for making this happen and giving me the opportunity to be here. So the aim of this talk is to understand the slide, basically. And so in particular, I want to say a little bit about what we call the univalence maxim, because the word maxim is really underused. It's supposed to kind of say something about how univalent mathematics is kind of cool when we want to look at categories. And then the kind of application case, the second part of the talk, is to when we apply this to the case of double categories. And so why double categories? Because they're trivial enough that they're like actual concrete examples out there in the world, but they're non-trivial enough so that like when you actually study this, it's still interesting. And just to like repeat this message, like formalizing categories is really cool, and I encourage you to do it. And we also do it as part of this project. But for this talk, I really want to focus on this part. So I want to focus on how kind of univalent perspective can be useful to understand categories. Now, this is an audience at the conference called HoTT-UF, so you're probably really into univalent math and you already like it and so on. So I don't really have to convince you that univalent math is cool, but you might have, I don't know, colleagues, office mates, neighbors, family members who might not be so convinced. And so please share the message. If you meet a category theorist, maybe this might be the entry point into univalent math. Who knows? All right, so let me start with the first case. So this is kind of like a warm-up case. Wait. I missed the joke, sorry. But okay. So let me start with the warm-up case. A category is kind of defined in type theory using like a bunch of, I don't know, pi types and sigma types. The only thing I want to mention here is, of course, I work in univalent math. And when I use the word category, I really mean category, unlike Mathieu's excellent talk yesterday. Where is Mathieu? He's not here anymore. But yeah, so when he said category, I meant infinity category. I really mean one category. So I will always insist that this thing is not. No, this one was better, but it's not connected, right? What? How is it off? I was using it.
Yeah, I think it's deactivated.
Sorry. Okay, my fault. Anyway, yeah. So I will always assume that the HOM are really sets. And I won't like repeat this for the higher categorical versions because then the definition gets too long, but I will say it once and for all. Whenever I define some kind of categorical structure, the highest level of morphisms are always assumed to be sets. The ones below can be interesting and different. All right, so when we know what a category is, when we have two categories, what does it mean when they're identified? What is the identity between two terms? In general, I can't say much, but there are two cases where I can say a lot. Namely, if I additionally assume that the objects also form a set, I call this a set category. And in a set category, I know that the identities will be precisely what we think of as isomorphisms. And we already just saw in the talk, like 10 minutes ago, that it can have this additional univalence condition. So the objects are not set, objects are the isomorphisms of the category. And in that case, the identities will be equivalences. So this is, in HoTT, this at least goes back to like more than 10 years by now. In outside HoTT, this was at least already kind of observed by Rasekh, which in something that we now call the Rasekh nerve, or like other quasi-fine diagram or something like this. Category theorists also think of this as thinking of the 1-1 category of categories versus the 2-1 category of categories, where the 2-1 category has also natural isomorphisms, so we get equivalences. So there's different perspectives on the same thing. Yeah. Scott? Good. The key point I want to make is that both matter. right? So the default, by default, we would use categories up to equivalence, and that's fine if we have a universal property or something. But there are situations where we really care about things in a stricter way. So when we want to talk about the set of objects of a certain category, this comes up. In particular, here in this context of this audience, in categorical semantics, for example, we don't just want a pullback. We really specify pullbacks and want some compatibility and so on. And there it's a situation where it's not enough to just work up to ISO. We want up to something stricter. So depending on the situation we're working with, we want both, but they don't include each other. So set categories and univalent categories, they both live inside this bigger cat. They have an intersection, which is kind of these categories without any automorphisms. But yeah, they're just there. So let's look at an example that is slightly less trivial, a two-category. So I'm not going to define two categories explicitly anymore, because that would be too long. But overall, it's roughly like a category plus two morphisms, which also compose associatively and unitary. And for two categories, we have way more notions of when are they the same. And I can at least think of three. So let's focus on these. So I can ask myself, are two categories isomorphic, or are the underlying categories equivalent, and the two morphisms are just bijective, or do I have like a biequivalence? Like, so the Hom categories are equivalent, and I have some kind of essential surjectivity. And now I can ask myself, can I, in this context of univalent math, construct some notion of two category so that if I look at it in the universe of two categories, the identity will exactly be these kind of equivalences, right? And so for case 1 and 2, I just use my category knowledge and repeat. So I say, I want, if I take everything to be a set, objects, one morphism and two morphisms, then the identities will precisely be the isomorphisms, fine. If I make the underlying category to be univalent, then my equivalence will be exactly some kind of underlying equivalence. And then there's also a notion of a univalent bicategory. And a univalent bicategory is like, so it has the objects are the equivalent, the equivalences, and every of the Hom categories will be univalent. And that is exactly, has kind of biequivalences built into the structure. But notice here something funny happened, right? So in the first two cases, I have two categories. In the last one, I mentioned a bicategory. I don't get a two category anymore. I have to like relax the structure. And it's not too hard to see why. So in order to define my univalent structure here, I need to have the fact that my one morphisms are the isomorphisms of my two morphisms, when I think of it as a Hom category. And when I make that assumption, then automatically they will usually not be zero type. So they will not have a category. I really have a one type of one morphisms, and I need to add the coherences into it. So I have a bicategory. So in some sense, this kind of equivalence forces me to relax the categorical structure and add coherences. It's kind of like a fun fact. And so now this allows me to make sense of like I said, what we call a univalence maxim, which is kind of saying that in a univalent setting, I can take a categorical structure, I can take an equivalence that I like, and I can define my categorical structure in a way so that the identity will precisely be the equivalence I started with. And sometimes I have to like appropriately weaken my structure along the way. And so this is kind of like the diagram that we get between category theory and univalent math. And we just saw an example of this. So I want to define, I'm in two category theory, I know what the two categories is, I know what biequivalences are. I want to define in the univalent world the notion of a bicategory invariant under these biequivalences. But this forces me to know exactly what the coherences of bicategory theory are. All right. How am I doing on time? Oh, wow. That went much faster than expected. Great. Okay, so it's good to take a break and see if any questions, because that's like the first half. Are they allowed to ask questions in the middle, or you are, right? Yeah. I see, yeah, true. There's one question.
Maybe to double check. So if the set category is what's called strict category.
Good point. So yes, I think in the original paper, strat categories are also called strict categories. I am personally not the biggest fan because univalent categories are strict, actually, right? The composition is it's associative and unital, right? It's not like I know the motivation because like there's like the objects kind of like stronger, but it's not like non-strict per se. So I think the word set category is more expressive for what it actually is. Yes?
So univalent set categories are rather rare, and are they not exactly what is called skeletal in the classical structure?
Skeletal would mean there are no isomorphisms, I think, right? Whereas, I mean, if you have two objects and one isomorphism between them, that is a univalent set category. Yeah. I mean, we can talk about it, but like the way I would think about it is you cannot have any loops, right? You want the type of objects to like be a set, but you also want type of objects to be isomorphisms. So, sure, yes. Yeah. Yes. It might be. I mean, it's stronger than. I mean, I don't know what. I guess it depends on which definition of skeletal we're working with, but okay. Yeah. No, exactly. I mean, I agree. The intersection is very trivial. That's the point, right? The point is that they actually don't intersect, so they're both important in separate ways. That is actually the point I want to make. So in that sense, we agree. All right. So let me move on. So I want to now focus on the case of double categories. I will not assume that you know what a double category is, but I also don't want to define it explicitly in detail, so let's see if we can do this. So first of all, why would we even care about double categories? Double categories naturally arise when we have a category, like we have some kind of cool objects, but then just have too many morphisms. They have two types of morphisms that you care about. And this actually happens a lot. And I tried to come up with a bunch of examples in different areas of math and computer science. So wherever you are, you will find one of these examples appealing to you. And so in this case, what we want is a framework where we have objects, we have two types of morphisms, and we have a bunch of structure which explains how these morphisms interact with each other. And that's called a double category. A precise definition of a double category, a strict double category, can be given as a category object in the category of categories. If you know what that means, then there you go. But if you don't, then, I mean, more explicitly, you can start by saying there's objects, there's horizontal and vertical morphisms that depend on the objects, and there are these squares which kind of explain how the horizontal and vertical morphisms interact with each other. And then there are a ton of compositions, identities, a bunch of associativity and unitality. And the reason I separate out the unitality and associativity conditions is because there's a variety of double categories, and the variety depends precisely on how strict these are. So some notions of double categories, this is super strict. Some are like more relaxed. And so depending on what choices you make, these two kind of are the determining factor. So to give you a little bit better sense of these kind of this data, here's like maybe a more kind of helpful diagram which captures the essential data of a double category. So again, I have objects, I have horizontal and vertical morphisms, I have squares, and then I have all these compositions. And then I have to make choices for, like I said, associativity and unitality. All right, so if I have two double categories, in how many ways can I ask myself whether the same or not? And there are actually a lot. So if you look at the literature, you will find many, but I want to end this talk in like 20 minutes or so, so I will only focus on 3. And let's focus on like first isomorphism, which is like always like the easy test case that we all know. Then another case that I want to look at is a so-called vertical equivalence. And there's an analogous horizontal equivalence, but it's focused on vertical equivalence. And it just means that if I look here, if I just restrict to the first column, I have a category. And if I restrict to the second column, I also have a category. And so I'm saying a functor is an equivalence. If I restrict to these two categories, I have equivalences. That's all. And then there's this last notion of what is called a gregarious equivalence. And that's just like kind of an explicit. It just can be described in terms of the double category itself, and it's kind of nicely symmetric in both directions. So you have a bunch of conditions that, like, it's a bijection on squares and essentially surjective, and some condition on the horizontal and vertical morphisms. And so what we could ask ourselves is, okay, how can I define a notion of a double category in univalent foundations so that the identities of that thing will precisely be these type of equivalences? And the first one, I hope everybody knows already, but the other two might be a little bit more tricky. So yeah, the first one is clear. We make everything a set, and we're done. Very nice. How about the second one? So for the second one, things get tricky. Let me come back to the diagram. So here in this diagram, if I want to have an equivalence, like identity to equivalence, then this underlying category should be univalent, right? So because it should just be seen as up to equivalence from the perspective of type theory. So this column should be univalent. This column should also be univalent for the same reason. But then I'm in trouble, because what can I say about this row? I now have a row where like this is a one type and this is a one type, so I will not have a category. My composition runs into, yes? 5 minutes, cool, no problem. And I see, this looked like a question, to be honest. Okay. And so what I have to do is I have to relax my structure in one direction. So I'm forced to like relax my composition in the horizontal direction and add associators and uniters. So what I need is a double category where one direction of the composition is strict and the other one is weak. Turns out people have already done this. There's various textbooks that one can look at this. It's called a pseudo double category. The name is not very descriptive because it doesn't tell you it's only pseudo in one direction, but such is life. And then, so what you can do is then put it into a type theory, formalize it, very nice and good. And then you conclude that indeed the identities of univalent pseudo double categories correspond to vertical equivalences. And if you flip things around, you get horizontal equivalences. But notice pseudo double categories classically seen are still like some kind of categorical structure. So I could still define a notion of pseudo double set category, which is a pseudo double category in which everything is set. And for that, I get another like different notion, which is like invariant under isomorphisms. Right? So for every notion, we get also additional ones that keep coming. It's kind of fun. How about the last case? So in the last case, we have gregariance, univalence. In this case, kind of if we take the previous one as motivation, we have conditions in both directions. So we would expect that we want a notion of double category where composition is weak in both directions. I have looked around quite a while trying to find something like this, but I've come to the conclusion that this doesn't exist. Like there's no literal textbook or paper where like, here's a definition, objects, morphisms, discoherence, this. I couldn't find it. If anybody knows, please tell me. So we have kind of reached the end of the literature. It's kind of fun. So what do we do? There's a cool trick. There is a notion of what is called a double bicategory. A double bicategory is not a double category, but it's kind of like a double category. It's due to Verity in his thesis, I think, from the 90s. And it's kind of like this very explicit ad hoc thing defined. I think the definition is like 7-8 pages long. And it has kind of interesting, it looks like a double category in a weak form, but has like extra information. And so I would think of it as a kind of like pre-double category, or maybe like a flagged weak double category. And what we realized is you can kind of adjust it to what we wanted. Right? So a double category, which is exactly weak in both directions, and then conclude the main result. But this, of course, is okay, it's nice, but also leaves you a little bit unsatisfied because you have this like other notion of a double bicategory, which is kind of separate from the whole double category literature, and they don't fit together. And turns out univalence is again a place where that kind of brings all of these together and makes sense of it. So let me like say this as my like last cool fact of the talk. Namely, okay, we have all these notions, and classically speaking, it's clear that everything that is strict will embed in everything that is not strict. And the less strict you get, the more you have just embeddings. But univalently, this is completely false. You cannot embed just things univalently into each other. You only have this in the classical world. And turns out Verity double bicategories are exactly what you need to actually get some kind of common playground for various univalent notions. It's like a really cool fact. And this I didn't know when we started this, but it's come out of this. So in general, what we get is like a diagram like this. So here you should break up this diagram into two pieces. So there's this top triangle. So in the top triangle is everything that has isomorphisms built in. And that is in some sense the classical picture, right? Because if you just define things in classical math, it will automatically be isomorphism invariant. And that is like this top part. And here in the bottom, we have like the univalent pseudo and weak double categories, which are exactly have their own equivalences built in. but they don't embed into each other. Like there's no way to go from a univalent pseudo-double category to a univalent weak double category in a way that is like just like a embedding. However, they both nicely fit into univalent verti-double bicategories. So it's kind of like big enough to incorporate these two different notions at the same time. And this is like I said, as far as I know, nobody in the double category literature had like a sense that these kind of connections existed in this way. All right. I'm out of time, right? Or no, I have still 1 or 2 minutes. Yeah, perfect, awesome. So let me end this talk by saying where can we go from here? First of all, one thing we would like to have is to put these univalent structures into categories as objects. So for example, we can put univalent pseudo-double category into some kind of bi-category. The problem is if you want to go higher than that, if you want to look at these weak versions, then we have to work at tri-categories. And we don't know how to do this yet. It's a pain. Tri-categories are big. Another cool fact of this is double category theory plays a really crucial role in formal category theory. So specifically the double category prof is super important. We now have various formalizations of prof, both with set categories and univalent categories. And so this is kind of a good thing to go from here. And yeah, so now hopefully this slide makes sense. As I said, the whole aim of the talk is to make sense of this one slide. I don't have anything else to say. So hopefully maybe this slide makes more sense now. Yeah, I have the relation between univalent math and category theory. And I have now various kind of double categorical notions that have kind of their equivalents built into the definition. And with that, I thank you for your time.
Questions?
Just a short remark, but your talk suggests that maybe we should arrive to a chemical classification of categories of the different variants of categories, double categories.
Sorry, what kind of classification?
Chemical
chemical.
Propane.
Oh, like
propane,
in chemistry.
Methane, ethane chemistry, yes.
Well, I'm not a chemist, so I don't know. But if yes, why not? I mean, I guess it is good. I mean, especially in this double category picture, I think it would be very valuable if people more seriously consider the equivalence that they are considering when working with stuff. I mean, I can see for categories it's kind of an overkill because you have two choices and usually it's fine. But especially for double categories, there's this extensive literature, and whether you're working with double categories up to, let's say, horizontal equivalence or gregarious equivalence changes their behavior, and the kind of results you prove are different, and people don't explicitly, they just say double category, right? Because there's no other way to say this. And so, and I would say, yes, so in the sense of chemistry, I guess the properties change depending on which kind of equivalence we focus on, so maybe that's a good angle.
It would be easier to know what we are talking about without to learn a lot of vocabulary. I don't know.
I mean, it goes both ways, right? I mean, I guess the extreme version of this is to say, okay, I want to work with a set which has an operation that has an inverse and that has identity and blah, 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 or say a group. And you probably would not say we should just not say group, right? But on the other hand, too much vocabulary can be frustrating too. Like I said, so it depends on how complicated the object is, right? So for categories, I'm open to it. For the more high categorical stuff, I think it would be really helpful to clarify the picture.
I think Ulrich was first.
Ah.
Oh.
So yeah, thanks for the talk. Have you looked at pro-aero equipments and how that might simplify the picture a little bit if you restrict to double categories that are pro-aero equipped?
I think that is one place that we want to look at, but we have not. Right, so that's I guess the short answer I could give right now. Because I think this is also a kind of indirectly. I think this goes in this direction, right? Pro-aero equipments are exactly what you want for so this is. I mean, what else is there? It's more future direction. So I agree, but it's not something that we have done actively yet. No.
I wonder on the page where you're comparing the classical picture, yeah, this one here,
Mm-hmm.
how many of those dotted arrows are actual maps? I mean, in what sense? I'm wondering in what sense you meant this as a formal statement. I mean, because
The
presumably some
the
of them,
dotted arrows means that classically there is an embedding, but
I
not
mean,
univalently. There's
but
nothing.
such maps might exist in some cases, like various completions, right? So like set categories. I can.
Aha, so we have not really looked at completion operations. That I agree, but this is
Because this could be a formal statement, as
yeah,
in
yeah,
these
this-
maps exist and
yeah.
are not embeddings. I wondered if that's what you meant.
well, no. I mean, the formal statement is that if it's dotted, it exists, but only classically, not univalently. That's what I mean with this. It is formal.
What does it
But-
mean to exist univalently? Do you mean just in type theory, or is that a condition, a univalent embedding?
Well, I mean, in the so the kind of arrows that are full, that means that it's just an embedding of universes, right? So it's like
so it's just a property. In other
yes,
words, yeah,
it's just
it's
a
just
property.
a property.
But
right?
these ones, they don't. I don't know. I have no idea if they exist yet in the type theory.
There could be maps. That
But
that
yeah,
are-
there could be maps. I mean, I don't know. This one, I don't know. This I mean just literally classically, like outside. What you would expect, I agree, should be completion operations. So there should be like a way to complete whatever you
And
take.
you could expect that they are literally not embeddings, right? So
But the completions would not be embeddings, right? Because I mean, even like for the example of categories, right? If you take, you can rest complete set categories to univalent categories, but it will not be an embedding, right?
right.
Because
This is my point: is that you could actually view them and take this literally as this is additional structure.
Yes.
By saying that.
yeah, but we have not worked on completions yet. This is also one of the. I could have mentioned this here, but yeah. But definitely completion operations are one next place to go also for this double category stuff.
Sorry? Okay.
Huh?
Sorry, I can't see if people have their hands raised, but I had a question from the online audience. If you can hear me.
Yes.
It's about the same slide as the one we're on. So I like thinking about the category of double categories as the tensor product of cat with itself in locally presentable categories. Is there a way to maybe decompose all these various flavors of double categories using set categories or univalent categories? And
I mean, this is okay. Let me think. So my guess would be that these ones, like the univalent pseudo double categories, is it? I mean, I don't know exactly how the tensor product does with respect to, because I mean, if you tensor, this is true for double categories, but for pseudo double categories, the composition is weak in one direction, and the weakness comes from the squares. How can I build in? I mean, I guess if I used some kind of like, I took categories, and then 2-1 categories. So I took the, I took a notion
So
that I
I
could take
kind
a
of naturally-
2-1 category. And so where I have like
Yeah,
weakness
I
in
kind
one
of-
direction, and then I took a 1-1 category strict, and then tensor them, then presumably this might be what you want.
yeah, so the tensor product works at any level of n1, including infinity 1, right? So we could fix something high enough so that all of this.
Well, that's what I'm saying. Like if you, your statement was that if I tensor cat 1-1 and with itself, I get strict double categories. I think that's what you said.
Yes.
Yes, and my
that's one
statement is
yeah.
presumably, like my guess would be if you take cat 1-1 and tensor it with cat 2-1, then maybe that would give you like pseudo double categories. And if you take cat 2-1 with itself, then maybe you get some kind of weak version. But that's a guess.
Yes, and then
like
maybe
that's
the univalent thing comes in.
Okay, for the univalence part, okay, I could see that. But the problem with these, these gregarious ones, they're in some sense, they seem to be really just using the double categorical structure. I don't know if I can decompose this. I'm not sure. My guess would be no, but I would be open to it. But the one for pseudo double categories, I could see decompose here, because you're taking only one direction. Like you're ignoring one, you're just taking the other. So yeah, sure. But for the gregarious one, it's kind of tricky. Like it's not, I mean, I didn't mention this in the talk because I would be too late. But there's this whole business of mates, and that's where the word gregarious comes from, right? There's all these like mate business that matters, and I don't know how to decompose mates. My guess would be that you can't do it. But I mean, I'm happy to discuss this more.
Okay, thank you.
Okay, sorry, another question.
Okay. So there's this known fact that when you look at bicategories and you consider lax functors, the notion of lax functor is not invariant under equivalence of bicategories. So if you post-composition with an equivalence of bicategories, does not induce an equivalence on lax functors. And it has always seemed to me that this is because lax functors did not preserve isomorphisms, but lax functors between univalent categories in the univalent context should. So what does this perspective that we should think univalently with categories tell us about how we should think about lax functors?
That's an amazing question, but I don't have the answer already.
Okay.
But I'm happy to.
Thank you.
I mean, if somebody has a comment on this, I'm actually super interesting. I'd like to hear more, but I've not thought about this, so don't have an answer ready.